Cool. So this is the eval workshop. That's the embodied vision, actions, and language workshop. And I think a lot of you are amenable to the sort of philosophy of this workshop, but it's basically that a lot of really exciting work has been made in the space of adding language to vision applications in the last couple of years, particularly work by like Peter Anderson, who's here with us today on vision language navigation that sort of kicked off work on combining language and vision and actions, where actions are moving around in some kind of simulated environment. And we wanted to kind of bring to bear some additional considerations that happen when we try to bring robotics into this mix. Like if you actually wanted to put a platform into the real world, suddenly there's a lot more constraints than just putting your body in the right space, right? There's sensor drift, there's using an arm to actually manipulate objects in the environment, there's appliances and other like state changes that have to be considered. And your actions have consequences, right? As a navigation agent in a simulator, you can always sort of back up and reverse whatever you've just done. But if you're a robot and you knock a glass off a table, it shatters and like you're in trouble. There's no way to take it back. And so to start to address that, we introduced the Alfred dataset. That's Mohit Sridhar, who's here as well, his primary work. And that introduces some of these constraints, like there are objects that can have state changes, there are things that can be done that can't be undone. But of course, we simplify a lot of the real difficult robotics considerations in that data set. We will have some talks from people who were contributing primarily to the Alfred task, so some task planning and model papers. Ruzba joked on Twitter yesterday that our winning team from Van Quang, who's here as well, achieves 4.5% success, which is a 10 times improvement over the baseline of 0.04% success. So 5% doesn't seem like a lot, but this is like a really crazy hard task. So it's awesome that we got such a huge improvement. It'll be the 10th talk today, so looking forward to seeing that. And we have secured some prize money for that. So we'll release at least $500, potentially more, to Van Quang and his team for that. And we hope to see more submissions to the Alfred leaderboard moving forward, because it's very clear that there's a lot of headroom left. The human performance is like 87%, and we're barely clocking 5 now. So without too much further ado, I'm going to go ahead and move us on to the paper stage. So I'd like to have the paper presenters go in order of the paper number from the poster session. So if you go to the eval website, which I'll drop in chat just real quick, you can see the poster session number order. We'll also use that in our gather.town instance to separate out where the discussions are happening. Each poster number has a sort of little section in the physical map to go walk to and ask questions. We'll talk about that a bit more afterwards, but let's start out with a cordial sync, which Unad is here to present, and I'll turn it over to you.
Thank you. Let me quickly share my screen. Cool. You see the presenter view, right? The full screen.
It's good.
Cool. Hello, I'm Unad, and very delighted to kick off the session with an overview of our work, a cordial sync going beyond marginal policies for multi-agent embodied tasks. We are focused on 2 major contributions. First is a decentralized multi-agent RL method, which goes beyond a single marginal policy per agent. Second, we introduce a task of furniture moving, where multiple agents relocate a heavy furniture item to a desired goal. In this example, the blue and red agents are tasked to move a heavy television to a yellow table. This task, different from previous works, requires coordination at every time step. Previous multi-agent methods generate a single marginal policy per agent. Here, agent 1 and agent 2 generate marginal policies pi 1 and pi 2 respectively. Since each agent acts independently based on its own policy, the effective joint distribution that previous methods capture is the outer product of marginal policies. Such a joint distribution is bound to be rank 1, which is a severe limitation. To move beyond this rank 1 constraint, we introduce cordial sync policies. Instead of a single marginal policy per agent, we have multiple policies. Using communication symbols, mixture weights alpha are generated. We suggest an easy way to synchronize the sampling from alpha across the agents. With this, the agents can jointly agree upon which of the M strategies they wish to deploy. Choosing actions through this synchronized sampling process implies that the agents can capture a mixture of marginals joint policy. This joint policy is high rank and hence represents complex policies for highly coordinated tasks, such as furniture moving. The video might have some issue across Zoom, but I'll still play it. Here are some coordial sync agents deployed in an unseen test episode. They reposition themselves to fit in the narrow space behind the sofa, carry the TV over obstacles, coordinate their actions effectively to move it over the yellow goal object. Here is another rollout in a different test scene. Note how the agents reposition the TV and successfully complete the episode. Our code, data, and pre-trained models have already been released. For additional details on grid-world agents, 3 agent setups, interpretation of communication, policy visualizations, please see our paper. We are very happy to discuss more during the workshop or in Thursday's spotlight session. Thank you.
Awesome, thank you, Anat. Let's turn it over now to Ming Zhao for paper number 2.
Okay, can you guys see my screen? Can you guys hear me?
Yes.
Yes.
And hear you.
Okay. All right. Okay. I'll get started. Hi, everyone. My name is Ming Zhao, and I'm going to present the paper titled "On the Evaluation of Vision and Language Navigation Instructions." So the problem of vision and language navigation, or VRN, has gotten a lot of tractions over the past few years. In the setting of VRN, a embodied agent is asked to follow a given natural language instruction and reach the pre-stated goals. The problem of navigation instruction generation is the exact opposite of VRN, in which we already know the path or trajectory, and we would like to generate instructions for the given path. And the generated instructions have been shown to be very effective for data augmentation and pragmatic reasoning for VRN, and they have been widely adopted in many studies in VRN. However, perhaps very surprisingly, the actual human performance of these generated instructions has never been evaluated. We do not know whether these generated instructions are correct or followable. In addition, the efficacy of these automated evaluation metrics that are used to evaluate and develop these instruction generators has never been established, and we do not know whether metrics such as BLUE or CIDR should be used or not. So our paper is exactly trying to answer these questions and provide a solution. So first, we carried out a detailed human evaluation of instruction generators, several instruction generators, and compared them with human wayfinding performance. The human performance is highlighted by the purple box at the bottom, and we found that these instruction generators have significant headroom to improve compared to human performance. And second, we compared human performance, human wayfinding performance with the scores from automated textual similarity metrics such as BLUE, METEOR, and CIDR, and we found that they are generally ineffective for evaluating generated instructions, with only one exception for the SPICE metric. And in this table, we show the Kendall's-Tau correlation at the model level, and only SPICE shows positive correlation with human performance. So to address these problems, we propose a model-based approach, and we found that our model-based score actually correlates better with human wayfinding performance than any of the automated metrics, including SPICE. And here on the table, we show the instruction level Kendall's-Tau correlation. So these are at instruction level, which is more granular than the model level. And our score, our model-based score, shows better correlation than any of the automated metrics. And in addition, because our model-based scores do not require any reference instructions, so we can use it to identify high-quality instructions for VLN data augmentation. And these figures basically show that the instructions selected by our model significantly outperform randomly selected instructions, basically showing that our approach is very effective for data augmentation. In addition, our model-based approach can also be used for the development of better instruction generators in the future. And of course, they can also be used for a reward for VLN agent. So that's the main point of our paper. Thank you.
Awesome. Thank you, Ming. Can you release the share screen?
Sure.
Thank you. So now we'll move to Peter Anderson talking about paper 3.
Okay, hopefully you're seeing my title screen. Is that coming through? All right, thanks everyone. So my name is Peter Anderson and I'll be talking about sim-to-real transfer for vision and language navigation. And this is work with collaborators from Georgia Tech. So the vision and language navigation task, as probably many are familiar, we're giving an agent a natural language navigation instruction in some visually complex environment, and we're trying to train or develop an agent that can reach the goal. And underpinning a lot of this work is a simulator that looks something like this, in that the environment is made up of panoramic 360-degree images, as well as a navigation graph, which links these images and basically indicates feasible trajectories that an agent can follow. So there's been a lot of progress on this VLN task in this environment setting. But what we actually focus on is what's the implications for robotics of the progress in VLN. And so naturally, there's a lot of issues to do with real-world sensing and localization errors, and even just integrating complex components that haven't been addressed in the navigation graphs. So what we aim to do is basically take a robot based on a turtle bot with an additional 360-degree camera, place this robot in a 325 square meter unseen office environment. This robot will have some kind of initial heading, in this case facing the window, and we're going to give the robot a navigation instruction. And having lifted a VLN agent trained in simulation onto this robot, our hope is that it can navigate to the goal location. And in particular, we also construct a simulation environment that's identical to the physical environment we're evaluating on to establish the sim-to-real gap. So there's a lot of problems to overcome in terms of making this leap from simulation to the real physical robot. The main challenges and I guess methods we use are domain randomization to overcome visual domain differences. Secondly, we develop a sub-goal model to basically remove the reliance on the navigation graph by predicting nearby waypoints for the robot. And thirdly, we use standard ROS components for SLAM and navigation at the low level. And so the kind of outcome of all of this is something like this. So at the left-hand side, you can see the images from the robot, the forward-facing camera, and then below that, the panoramic image, which is taken at a lower frequency. At the top right, you can kind of see the robot moving around the environment as it's starting to navigate around the chairs. And then in roughly the middle is the map that the robot's using. So in this setting, we've given the robot an occupancy map as well as a navigation graph to help, which is indicated by the blue dots. But we also consider a setting in which there's actually no pre-mapping of the environment whatsoever. And in all the settings, the visual aspects of the environment have never been seen before. And so very briefly, what we find is that the sim to real gap is reasonably small if we're able to do occupancy mapping and build a navigation graph in advance. But that actually gets much wider and is much more challenging with no prior mapping whatsoever. And that's primarily due to differences between the predictions from our sub-goal model and the actual navigation graph. So that's our work, and I look forward to chatting with folks some more in the poster session. Thank you.
Really cool stuff. Thanks, Peter. Exciting to see Peter still working on VLM, taking it all the way to like the actual robot platform. It's very satisfying. All right, now it's Felix with paper form.
Yeah. Hi, so my name, as Jesse just said, my name is Felix. Today I'll be presenting our work, Modular Networks for Vision Language Navigation. We're all at CMU, hence the red. It's Xiaopeng Liu, Nariaki Kitamura, and Gino. So Peter just presented, he just discussed VLN and specifically the R2R data set, and that's what our results are based on. So VLN, as most of you probably know, VLN is a hard problem. I think for single models, the success rate of getting within 3 meters is about 50 to 60%. There's also a decent generalization gap between seen and unseen environments. In R2R, there's a seen and unseen validation split, where the unseen validation set has environments that are not in the training set. Solutions to both these problems have been proposed, like speaker follower, which was mentioned in an earlier talk, where you use back translation to augment the data. This requires 2 models. We wanted to explore an approach which only had one. You could also pre-train using an external data set like a panoramic caption set, but this requires an external data set which is well suited. And there's also maybe out of like a domain transfer could be an issue. And the final thing is using higher level segmentation features, which has been shown, to reduce the generalization gap, but there is a slight the performance on scene environments is slightly lower, but the authors talk about this. So our motivation was to build off of this, build higher level features, but using the existing data. So to have a better usage of it, and to also add in interpretability by splitting it into modules. This is a work still in progress, so we appreciate feedback. I also, just FYI. Okay, so how are we proposing to do this? The idea is to learn skills like underlying skills, for example, recognizing objects, how to ground action and vision, and then learning other things like adding on top of that later and adding language and predicting actions. So the idea is to have a 2-phased approach. The first would be pre-training on our data by adding additional objectives, which we see on the right-hand side, predicting things like, it says bow, but what did you really say is a set of classes for the image, doing that for the viewpoint and the scene so that we learn those high-level semantic segmentation features, and then building on top of that and adding in a kind of temporal task, like grounding action and the visual feature together with the binary classification. What we do is we take in that scene feature that we've learned through these the prediction task, and we try to predict if a target action and sorry, I'm a little nervous. We take in that scene feature and we feed in this target action, and we try to predict if a target feature, like in the panoramic view, if this action from this position would lead to that. And we feed in noisy actions from time to time. We try to predict if those correspond. We use this as a pre-training step. And once we have this representation trained, we use it as an encoder, and we we learn the language and the decoding on top of that. So the action portion of it didn't work well. It was very noisy. So we just kind of debugged by removing the object detection portion of it, and just fed in the image features directly into that valid path prediction task, where we try to predict if an action leads to a given state. We pre-trained for about 4,000 epochs. There was a very slight performance improvement. Not sure how meaningful that is, but we think it's meaningful enough to keep working on it. So in short, we propose adding some kind of like learning grounding beforehand before we learn the language. The results are far from complete. We'd like to maybe add back in the object detection, either through directly injecting it or maybe tweaking how we learn it, adding in things like color, and maybe an alignment task that requires history. Looking for, so the idea was to get some feedback. So you can, I'd love to speak to anyone at the poster portion. And if not, here's my email. It's flabell@andrew.cmu.edu. Thank you for your time.
Thanks, Felix. And now we'll hear from Matt Chang for paper number 5.
Okay. Am I unmuted now? Yes, okay. Thank you all for having me. So I'm presenting on our paper, Semantic Visual Navigation by Watching YouTube Videos. I want you to look at the 2 pictures here and imagine you're looking for a bathroom in one of the 2 restaurants. And even though you can't see a bathroom or a sign indicating there is one, I think you'll agree that going straight in the image to the left is more likely to lead you to a bathroom than going straight in the image to the right. And this is mostly based on implicit cues in the scene. Our paper seeks to learn and leverage these sorts of semantic cues for finding everyday objects like beds, chairs, couches, and tables in novel environments. A common approach for learning these sorts of navigation policies uses reinforcement learning with direct interaction. However, in this paper, we pursue an alternative approach, where we mine for spatial co-occurrences in indoor environments by watching real estate tour videos from YouTube. This is passive data available on the internet with a lot of visual diversity in real environments. To this end, for this paper, we collected just such a data set. So as you can see, there's a lot of visual diversity in these videos from YouTube. We ended up downloading 1,387 videos for a total of 119 hours of real estate tours. And they're mostly one continuous shot, which will show a lot of object co-occurrence, as we would want to see. Even with this data available, performing learning for navigation policy is still a challenge. Unlike the data used for traditional learning from demonstration techniques, these videos don't come with action labels. The goals and intents are not known, and the depicted trajectories may not be optimal. So to tackle these challenges, our approach starts with real estate tours from YouTube. We use an inverse action model, which has been trained on random actions executed by the robot to pseudo-label image frame pairs with the intervening actions. Next, we label goal frames with an object detector trained on the MS-COCO dataset. With these pseudo-labeled actions and rewards, we can perform Q-learning quadruples, which allow us to perform Q-learning on our dataset, which will implicitly learn a function which utilizes these semantic cues for seeking objects in indoor environments. Given this learned value function, which predicts the nearness to goal, we perform the actual navigation with a hierarchical navigation policy. Without going into too much detail, the high-level policy uses the value function to decide where to go next, and the low-level policy uses classical SLAM and planning methods to achieve these short-term goals. In evaluation on a set of novel environments, our method is able to outperform exploration baselines, reinforcement learning, even when reinforcement learning has access to many more environments, and behavior cloning on the same video data set. Thank you for your time. For some visualizations of what our model learns and test time trajectories, you can see our project website or maybe stop by during the poster session. Thank you.
Thanks, Matt. Now we'll move to paper 6, which is from Leg.
you hear me and see my screen? Okay, cool. Thank you. I'm gonna share. All right. Hi, my name is Lake, and this is joint work with my mentors at Jonathan Bisk and Alex Polozov during my residency at Microsoft Research. We're interested in automatic instruction generation for egocentric skill learning. We believe that embodied agents need to not only be able to follow instructions, but also give them. Previous work has focused on simple navigation instructions and on language generation targeted at embodied agents, not humans. We take a different approach and target the creation of explainer modules that eschew low-level instructions in favor of more natural, goal-directed language. We achieve this in part with novel fine-grained state tracking to minimize extraneous details without forgetting the core properties of tasks. The baseline model, illustrated in monochrome, takes in action embeddings and observation features as inputs to predict language instructions as outputs. State tracking, which is illustrated in orange, augments the baseline model into the explainer. Specifically, the encoder is enforced to track per time step object states by means of additional input features. And the decoder is enforced to track object states corresponding to the end of the task by means of auxiliary tasks. The explainer can be trained without any extra human annotation on top of existing VLN benchmark datasets. In addition to this new model formulation, we propose a new object capture test to evaluate the accuracy and goal-directedness of these explainer-generated instructions. It evaluates the overlap of task-relevant object nouns between the generated instructions and human annotations in terms of precision, recall, and F1 score. We find that the explainer captures these nouns noticeably better than the baseline across most subgoals in the Alfred benchmark datasets. On the other hand, using Blue score as an approximation of fluency, we find that the explainer also outperforms the baseline. Upcoming work will evaluate the explainer on downstream agent training and human evaluation. Thank you.
Thanks, Leg. And I think Ahmed will be presenting paper 7.
Okay. Can you see my screen now?
Hi everyone, I'm Ahmed. I will be going to present our work Referred 3D, neural listeners for fine-grained 3D object identification in real-world scenes. Our contributions of this work are threefold. First, we introduce the novel task of language-guided 3D object identification in real-world scenes. As shown in the image, our goal is to identify the target object, here a table, which is referred by a language utterance. In our setup, we make two important design choices. First, the target object must coexist in the scene with multiple distracting instances of the same class, in addition to different class distractors. Second, we ground the problem directly in 3D space, and specifically, we use 3D point clouds to represent the scenes and their objects. To solve the above task, we introduce two visual linguistic datasets with discriminative utterances characterizing objects in 3D scenes. And thus, we develop a multimodal deep neural network that comprehends linguistic references made about these objects in order to identify them. In absence of other datasets, we begin by collecting natural language by deploying a reference game between two humans. First, a human speaker observes a 3D scene that contains a target object among its distractors and is asked to provide a discriminative reference for that target. This reference is used by a human listener who, given the same scene, is asked to identify the target. The resulting dataset contains more than 40,000 utterances, and human listeners were able to identify the target 92.9% of the time correctly. We further augment our natural utterance dataset with synthetic utterances that express spatial reasoning. Specifically, we create a corpus using a compositional template that considers 5 broad types of spatial relations among 3D objects. Here are some examples of SR3D. In our proposed architecture, first, we extract the visual features of each object and a linguistic feature for the utterance. We fuse them via a dynamic graph neural network that takes as an input their concatenated representations and explicitly encodes pairwise object interactions among objects nearby in a latent space. The final fused representations are passed to a shallow MLP that predicts the target. For this architecture, we also use two auxiliary classification losses that guide the visual and linguistic representations. Our main findings are the following. The explicit context incorporation in referred 3DNet gives a boost in the performance with respect to the list context-aware baselines of 7%. Using the two auxiliary losses in referred 3DNet improves performance by up to 3%. Here are some qualitative results using referred 3DNet. Thank you for watching.
Thank you, Ahmed. Now we'll move on to paper number 8, which is presented by Shoujo.
Hi, everyone. I will also be sharing a video of my work. So all right, I believe everyone can see this video. Yeah, let's start.
Sorry, is there?
Oh, I'm sorry. Did the audio not share?
I think.
Yeah, I think your video is muted.
Oh, that's stupid.
Yeah. So while sharing, I missed clicking optimize for video. I think you also missed clicking optimize, like share computer audio.
Yeah, there you go. Thank you, guys. All right, let's try this again. This video introduces the robot slang benchmark, a new real-world dataset for dialogue-guided robot localization and navigation. Let us first describe the problem setup. The goal of a robot slang trial is to find 3 objects in the maze in a certain sequence. The driver navigates the robot, and the commander directs the driver. On the left, you see the driver feed. On the right, you see the map provided to the commander. Crucially, neither the commander or the driver know where the driver is located at the start of a trial. Both are allowed to communicate with each other using only a text channel interface. To solve a trial, they must first localize the position of the driver within the maze, and then the commander must direct the driver to the objects within the maze. Here is an example of robot slang's vision and language navigation task in action. We make a simulation environment to recreate robot slang trials. To validate our simulation, we perform simple particle filter localization of the driver. On the left, you see the annotated map. In the middle, you see the actual map. On the right, you see the different driver feeds. The top driver feed is the actual live feed. The one below it is an annotated feed that separates the original feed into its constituent colors. Here we show that localization is possible in our annotated maps using these labeled forward feeds. Our final clip shows how we use our simulated environment to train VLN models. Agents have the supervision of a global optimal path planner and utilize actions provided by this teacher path planner to learn. Here we see our simulation in action. The robot is the blue dot. Particle measurements are sent out to measure the wall colors. The different color blobs represent objects, and the small green dots represent the discretization of the maze for simulative purposes. The yellow trajectory represents the optimal path to the goal and is used as a form of supervision. On the right, we see the dialog provided to the agent to perform the navigation from dialog history task. Hey, so we really, in this work, we made a real world robotic data set for vision and language tasks. I don't think I've seen very many similar works. I think a lot of work currently is grounded in simulation because VLN is such a hard problem. This is a data set that we will be releasing soon. And we were very interested in seeing whether models that are actually trained on these simulations can transfer to the actual work, to these actual real robotic platforms. So if anyone has any questions, please contact me at the poster session. And otherwise, yeah, let me know if you have any questions there. Thank you.
Thank you, Shorjo. Now we'll move to Kunal presenting paper 9.
Can everyone see my slides? Hello?
Yeah, we can see your notes too.
Let's see your notes as
Yeah,
well.
okay. Sure. Okay. So I'm Kunal and I'm from IIT Roorkee, and this is joint work done with some colleagues at GIST and IIT Roorkee. So we submitted the challenge paper to the Alfred workshop titled Improving Mask Prediction for Long Horizon Instruction Following. So the Alfred benchmark was presented to connect ecocentric vision language instructions to action sequences for daily household tasks. So the new thing that Alfred introduced in addition to existing VLN or VLN in continuous environment benchmarks was an addition.
We cannot see the bottom portion of the plot. Is it the same for other people?
Yeah, it looks like
it's
the bottom fifth or so of the slide is cut off.
Oh, okay, I can
Maybe
see.
you can exit full screen and this works, yeah.
Yeah, this is fine.
Okay, this one. Yeah. So, so one thing, additional constraint that the Alfred benchmark added was to add a localization task also for the agent, in which the agent needs to localize the object it wants to interact with. The localization problem is generally considered solved in previous planning tasks, but in this case, the agent has to predict a pixel-wise masks to perform any interaction action. So the baseline performance is 4%, indicating a lot of components, including the action prediction and the mask prediction, are missing from the baseline model. So this is an ongoing work, so we decided to first investigate how bad the mask prediction is. So currently, the baseline model just upsamples a joint vision action and language embedding to produce the mask. But the mask produced by this method is not of a very high quality, as can be seen in these 3 examples. The target objects are like cell phone, cannon, and pillow. So in one case, even the target object is very clearly visible. The baseline model inaccurately localizes it and also predicts a mask of a very sparse quality. And in the second case, the candle is occluded, so the agent is not able to localize it at all. And in the third case, the pillow is barely visible in the ecocentric frame. So the model produces just a random mask. So what we do is the first obvious step was to replace the deconvolution layer with the pre-trained FCN decoder. And after that, what we did was we make a gold action setting, in which what we do is we just give the expert optimal actions to the policy and just make the baseline model produce the mask, and the modified models produce the mask to see how much trajectories we are losing because of the mask prediction itself. So now 43% of the trajectories are covered if we keep the mask prediction of the agent, but 57% of the trajectories are failed only and only because the mask prediction is flawed. And that remains the same if we keep a FCN decoder, because the FCN decoder has been pre-trained on vision data set, so it does not have the capacity to upsample vision and vision language action embeddings appropriately enough. So what we do to counter this problem is to we just break down the mask prediction problem of Alfred into a two-stage approach. So what we simply do is we take an additional mask RCNN and train it on the expert action frames and the segmentation mask corresponding to those expert action frames, and just pre-train it and keep it frozen during the other training. And during training, what we simply do is we replace the task of predicting the exact pixel-wise mask by the task of predicting the target object. That makes it a bit easier to learn the model and also makes it faster for the model to train. So what we simply do is at test time, a model predicts a target class that it wants to interact with, and we simply take the mask corresponding to that target class and predict the mask with the higher confidence. So what happens with that is the quality of mask is very accurate, and also the localization is also not flawed. So the rest details are the same as the baseline model. And so now what we see in the gold action setting is the 17% of the lost trajectories out of the previous 57 have been recovered because of this two-stage mask prediction. And the overall results when this two-stage module is plugged in the baseline also improve on the Alfred benchmark. And some qualitative results on this is when the cell phone was not even correctly localized, the boundaries are also very fine, and the model is able to correctly classify the cell phone and identify a perfect mask and successfully accomplish this task. The same works for the candle, which is occluded by the spray a lot in this frame, but still the model was able to capture that candle even if its visibility is really small. And the pillow, which was totally out of frame, was also recovered in this. So in conclusion, this is an ongoing work, and this approach basically right now serves as a plugin for better action predictors. And if there is a model that predicts action even better than the baseline, the gains will be more than 1% or 1.5% that we currently observe here. Thank you, and this is an ongoing work, so I would love to interact with all the people in the workshop and have feedback on this.
Very cool work, thank you. So we'll have our final presentation now from Van Kwang's group, which is another paper that tackled the Alfred benchmark. This is the current leaderboard leader.
Yes, can you hear me? Just let me share the screen. Can you see my screen? Hello.
Yeah, you're good.
Yeah.
Okay.
But it's not in the presentation. Okay. No, it's
Can
good.
you hear me? Can you see my full screen?
Yeah, looks good.
Okay, cool. So good morning, everyone. So I am Kwang from Tohoku University. I'm going to quickly present our work, a hierarchical attention for the challenge, unthreat challenge. So first of all, let me summarize some takeaway keys making our work different from the baseline models. First, we use multiple scenario views at one-time step instead of a single view. And second, we use mask RCNN to track the features and mask for further predictions. And number three, we encode the high-level instructions aligned with the low-level actions during the training. And number four, we use a hierarchical attention mechanism to guide the visual features. And we also add the instruction deciphering decoder with only the language feature as its input. So let me go into the detail a little bit. First, for language encoding, we transform the task goal and high-level instruction into the embeddings initialized with the graph vectors. And the embedding layer is shared between them. And next, we use different LSTM to encode the goal embedding and instruction embedding separately. Note that every high-level instruction here is encoded independently. So for visual encoding, following the recent navigation task, we feed multiple frames representing for the left, right, up, down, and center views of the agent at one-time step into a pre-trained mask RCNN to to extract the bottom-up features along with its boxes, mass, and score for later mass prediction as well. And to learn the relationship between the objects, we use a simple cell attention mechanism from our recent work for each frame. And now at the time step T, we first map the high-level instruction into its corresponding low-level action during the training. And the instruction feature is used to attend both the feature at the object level, and then we obtain the weighted sum representation for each frame, and we perform the second attention. That is why we call it a hierarchical attention mechanism, to obtain a single vector representation for the visual features. And we concatenate it with the instruction features and use LSTM to learn the temporal relationship and making the prediction for the action. And if the action is kind of the interactive action, so we compute the mass loss based on the attention losses of the object from the center frame. And we also add the LSTM to learn deciphering the action, low-level action from the high-level instruction from only the language features. And here is the tables on the data set. So it can seem that our model obtained around 4.5% of the success rate, but still very far away from the human performance. So it indicates that how challenging the task is. And okay, that's all for my presentation. If you have any questions, so feel free to ask me during the poster section. Thank you a lot.
Thank you, Quang. So what we're going to do now is move into the GatherTown instance. And again, the plan is basically there's little sections you walk over if you're presenting to the labeled area that says like paper 1 through paper 10. And then you should be able to chat with people who have questions about the paper. If that turns out to work extremely poorly, I'll make an announcement that we're coming back on here and we'll instead just do a sort of one-by-one question answer session, but hopefully GatherTown works well. I'm gonna share the link to the GatherTown on the chat right now. It's also in the email that I sent earlier, but just so that our attendees who are here are able to move over to the poster session with us.
Also, it's worth just pointing out that in GatherTown, you can share your screen if you're a poster presenter, if you want to refer to things from your slides.
Sorry, I didn't get that actually.